Hi, my name is Mahalat Fikru, and the topic I will be discussing in Module 7 discussion is alkenes and alkynes. More specifically, I will be going over the electrophilic addition reaction mechanism to synthesize alkyl halides. For starters, what is an electrophilic reaction? Well, an electrophilic addition reaction is a reaction in which a substrate is initially attacked by an electrophile, and this results in the addition of one or more relatively simple molecules across multiple bonds. Alkyl halides are formed by the addition of an alkene and hydrogen halide during an electrophilic addition mechanism. As we can see below, the picture demonstrates the formation of an alkyl halide. We see an alkene being added to a hydrogen halide. Then it is yielded with ether, and then we have an alkyl halide. So the next thing that I want to talk about is the mechanism for an electrophilic addition reaction. So our first step in this kind of reaction is going to be an electrophilic attack. So our first step, during the first step of the mechanism, we see that 2 pi electrons from the double bond attack the hydrogen in the HBr electrophile, which is shown by a curved arrow, and I will later get to that in the next slide since there's an image. But the 2 pi electrons form a CH sigma bond between the hydrogen from HBr and a carbon from the double bond. So at the same time as this is happening, the electrons from the protic bond are able to move onto the halogen to form a halide anion. When the pi electrons are removed from the double bond, this makes one of the carbons become an electron deficient carbocation intermediate. What this means is that this carbon is now sp2 hybridized, and all the positive charge is contained in an unhybridized p orbital. So the mechanism continued. Step 2 is going to be the nucleophilic attack by halide anion. What happens is the formed carbocation can now act as an electrophile, and it is able to accept an electron pair from the nucleophilic halide anion. The electron pair becomes a protic sigma bond to create the neutral alkyl halide product of an electrophilic addition. So in the image below that I've inserted, we are able to see exactly the steps 1 and 2 being shown. The first thing is we see that the double bond is attacking the hydrogen, and the electron pair is being accepted to form the halide anion. So you're probably wondering, okay, Mahalat, well, how does this relate to Markovnikov's rule? Well, I'm getting there. But first, I wanted to go and give a refresher on what Markovnikov's rule is. So what it is when a protic acid is added to an asymmetric alkene, the acidic hydrogen is able to attach itself to the carbon having a greater number of hydrogen substituents. This leaves the halide group attaching itself to the carbon atom, which has a greater number of alkyl substituents. So in simpler forms, it just means that hydrogen is added to the carbon with the most hydrogens, and the halide is added to the carbon with the least hydrogens. So step 1 is going to be that the alkene is pronated and gives rise to the more stable carbocation. And step 2 is going to be that the halide ion nucleophile is now able to attack the carbocation, and this reaction yields the alkyl halide. So Markovnikov's rule continued. I'm just going to kind of go over the steps 1 and 2, but visualized. So in the first image, as we can see that there are 2 types of carbocations that are formed from the protonation of the alkene, one being a primary carbocation and the other being a secondary. Although the secondary is a lot more stable, its formation is preferred over the primary carbocation. And the addition will occur in a way that produces the most stable carbocation, after the initial protonation. And I guess just for extra knowledge, the tertiary and secondary carbocations are the most stable. And then step 2, we see that the halide ion nucleophile is attacking the carbocation. This reaction yields the alkyl halide, and since the formation of the secondary carbocation is preferred, the major product of the reaction in this image would be 2-bromopropane. So for the final slide before the sources, I'm going to be talking about anti-Markovnikov. And so what this rule is that it explains the addition reactions of alkenes or alkynes. The proton is added to the carbon atom that has the least number of hydrogen atoms attached to it, and we know when a compound would be, or excuse me, a chemical reaction would be anti-Markovnikov when a peroxide is added to the reaction, such as HOOH, ROOR, just things like that. But it is important to remember that the anti-Markovnikov refers to the fact that the reaction doesn't follow the Markovnikov rule, instead of it being a reference to an anti-addition in stereochemistry.